Hi, my name is Pomsu Kim, and I'm about to present you our paper, Misalign, Contrast, then Distill, Rethinking Misalignments in Language Image Pre-Training. This work was done at LG AI Research along with Yeonshik Cho, Jinyoung Kim, and Sewan Kim. Let's start then. Contrastive language image pre-training, or so-called CLIP, is a predominant pre-training method using uncreated image-text pairs crawled from the web. With the simple contrastive objective, influency loss, CLIP aims to make the distance between the representations of the matching image-text pairs closer than those of arbitrary pairs. Thus, this is a procedure where we pull the representation of the image and its text description together while pushing away the representation of all other text descriptions with the given batch. As a result, the image encoder learns from the representation of the raw text description without needing any data curation. Based on the vast success of random image augmentation in supervised learning, where the augmentation was a highly effective mean to increase data points, following works of CLIP have also attempted to apply image augmentation to CLIP. However, the text-agnostic random image augmentation procedure can cause various misalignments with its text counterpart. This can hinder training, resulting in suboptimal performance. Previous work in literature have dealt with this issue in different ways. First, SLIP excluded the supervision between augmented image and its text counterpart, conducting only self-supervision with the augmented image in a separately projected space. This method left a lot of room for improvement in terms of data efficiency. Next, while DCLIP considered the supervision between augmented images and text pairs, it didn't deal with the negative impact of the misalignments during training at all. Therefore, despite the huge training burden added, it led to suboptimal improvement in performance. UniClip also took the supervision between augmented images and text pairs into account. However, unlike DCLIP, they dealt with the possible misalignments by adding an external model that encodes the augmentation information during training. Though being fairly effective, it is still limited in that it adds burden during training and inference. To this end, we propose MCD. MCD is a novel distillation strategy that capitalizes on the continuous misalignments caused by text-agnostic random image augmentation. MCD consists of 3 steps: misalign, contrast, and distill. In the first step, we conduct the random image augmentation process to the input images. Since the augmentation is unaware to its text counterpart, various levels of misalignments occur during this procedure. Then, we learn the distance between image-text pairs using contrastive objectives such as the influency loss. Finally, we use a teacher-student network where the student learns the soft distance between the augmented image and its text counterpart. The distillation loss is composed of 3 terms that each treats different kinds of misalignments. The first term takes into account the misalignments caused in positive image-text pairs. For example, you can see that the random cropping of the image caused mismatch with the text since no dog is left in the remaining image. The second term treats the new positive alignments caused between negative pairs. For example, the cropping resulted in the remaining image to match with another text description in the batch, which was originally treated as a negative pair. The last term deals with the misalignments that originally exist in the dataset in cases where the captions do not fully explain the image or in some cases irrelevant to the image at all. In the main experiment, we pre-train MCD on the YFCC 15 million dataset and transfer it to various downstream tasks. First, we evaluate MCD on 11 classification downstream datasets. In both zero-shot and linear probing settings, MCD achieves state-of-the-art performance. Note that MCD does not require an additional memory queue for nearest neighbors or external models to encode augmentation information. Next, we evaluate MCD on the Coco caption and Flickr dataset to measure its effectiveness on multimodal retrieval. It can be observed that MCD also achieves state-of-the-art performance in image text retrieval. Finally, we conduct extensive experiments on MCD. For a more sophisticated evaluation on vision language task, we use the Sugar-Crawford dataset to evaluate the vision language compositionality. It can be seen that MCD outperforms previous methods in all 3 aspects. We also conduct an ablation study for the 3 loss components in our distillation. It can be concluded that each component positively contributes to the final performance. MCD shows a consistent improvement in performance when pre-trained on the CC3M dataset with the VIT-B16 backbone. Thanks for your attention.